Hello everyone, welcome to the EasyPower Tuesday Refresher webinar series. My name is Jim Chastain. I'm a solutions engineer at Bentley Systems. And as far as I'm concerned, this is one of the more interesting presentations and demonstrations that we have to offer. And hopefully you'll appreciate the breadth that we can kind of go through in the share. I do want to make a couple notes as we get started. In the handout section of the webinar, GoToWebinar control block, I've included two files. One is the PDF copy of the slides, and the other is the EasyPower Options Guide, which reflects the changes and affects most of the display I'm going to be running through today. So at some point in time, you may want to take advantage of that. So as we're in the habit of doing, I'd like to start with a couple poll questions. The first question is, does your company or team currently use Revit? Again, there's no obligation or liability, just trying to get some feedback from the audience. And what I'm suggesting is that especially if you've not considered Revit, or if you have integration with Revit, you haven't considered the EasyPower conversion tool, you may want to take advantage of some of the recommendations I have at the end of the session. Okay, let's leave this open another 10 seconds. We're close to a quorum. Okay, here's how folks have weighed in. So good. Most of the audience is open to some suggestions or good ideas. And then the second question is, have you heard or seen the EasyPower Auto Design tool presented before? And if nothing else, that's a little bit of a foreshadowing of where we're going with this presentation. So you may see some things that look at not only interesting, but familiar. So let's leave this open about another 10 seconds. All right. Thank you for participating. Here's how folks have weighed in. So this will be new information for majority of the audience. And then finally, have you seen EasyPower modules that are included in the new Bentley licensing scheme? And I say that so those of you that are not aware, EasyPower was acquired by Bentley Systems a little over a year ago, and within the last 6 weeks, we have managed to align our licensing system and delivery of the software through a Bentley supplied conduit. And in so doing, we've made some adjustments to the module listings for different packages. And so that's where the options guide comes from. There has been a notice sent out to the primary contact on the EasyPower books, if you will, if you've been a customer for any length of time. That person's received an email notice along with anyone that's been identified as purchasing contact. So the primary user and the purchasing contact have received a notice on the changes. And that, if you haven't seen that, or if you're having troubles, you may want to contact support at easypower.com offline. Okay, so again, this is new information, so I'm I'm glad you came. So Revit is an Autodesk piece of software for building BIMs, or building information modeling. It's a model-based process used to plan, design, construct, and manage buildings and infrastructure. And what you're going to see is it offers a multidisciplinary collaborative design process, including architecture, structural engineering, MEP engineering, and structural engineering for construction. And in the MEP category, there's HVAC, modeling, electrical, and plumbing. Now, what it amounts to is that EasyPower has the ability to modify, import, and make modifications to the electrical system as defined in Revit. And so what you're going to see when we get into the demonstration is I'm going to open Revit and look at the electrical distribution system for the plans in this three-story building. And that'll appear in the form of a project browser for the electrical system. That's been designed within Autodesk from a series of device library content they have with their suppliers. And so what you will find is that they do the mechanical layout and then the connections between the different elements. And the major benefit of that is the length that's going to be required for in a 3D world where those arrangements of devices are. We can also follow the evolution of a panel schedule, which will be detailed in Revit, imported into EasyPower, and then the operations that we're describing can be included on loads from panel schedules. And so the equipment properties are based upon, in part, this library that I'm referring to, which is a Revit domain. And we'll see in the system browser, the loads are all covered in panel or distribution systems, and they too have specific circuit properties. Now, the significance here is they may or may not have been sized for the load intended, and they may or may not have any calculations as part of this description. So that's where we're bringing in EasyPower tools. For those of you that don't know, EasyPower makes software for electrical power system analysis. It can be used for one-line diagramming, load calculations, short circuit analysis, arc flash, power flow, etc. And that information then will produce analytical data, analytical parameters that can then be exported back into Revit and allow the project designer to know that he's got information that will support the system as it stands and then accommodate changes as he goes forward. So one of the big steps in doing this conversion, as I understand it from people that are Power Revit users, is that it eliminates the need for duplication in creating a one-line. EasyPower will automatically, based upon the database that comes in from Revit, create a one-line diagram such as this. And from that, we can do the analysis of whether or not the elements have been properly sized, and then the bill of materials that results from that sizing. We can conduct a short circuit and smart duty analysis and identify areas where there could be problems based upon the parts selected. We most often would be involved utilizing the EasyPower tools for protective device coordination, arc flash calculations, and label generation. And significantly, more often than just a standalone EasyPower implementation, the benefits of doing power flow analysis and then delivering all that information back to Revit is considerably advantageous compared to the way the flow of information is currently developed in a Revit environment. So the same database can be used for additional analysis. We're not going to be getting into that. So just a point as we get into this, EasyPower Revit is aligned with the systems from 2017 through 2024. The Bentley EasyPower version 24 has just been released in the last 6 weeks. There's only low voltage support for low voltage components in this integration tool. And for those of you that needing single phase elements, you need to do those by hand because they're not included in the import process either. So what I'm going to do is look at the Revit electrical subsystem browser, and identify the elements that we want to track through the process of importing, implementing auto design, which will size the elements based upon certain criteria. We're going to do short circuit analysis to come up with fault current and equipment duty, make an attempt at coordination. And I say that because there's quite a few elements of multi-case circuit breakers which defy coordination, but we're going to give it a best shot. So with all that said, let's jump into Revit. So when you launch Revit 2024, you end up with access to several, at least in a developer mode, to several pre-drawn files. In 2023, it was a file called RME Basic Sample Project. 2024, it's this one which is some sort of a domestic housing project. What I've done is open up the project file that was used last year and saved it in my folder to be able to run it with 2024. So here's where we start. So as I launch the project, and this is being handed off to me by the architect or the engineers doing the building layout, I have the ability to look at different elements in my project browser. For instance, if I wanted to come up here under View, now I'm not a Revit power user by any means, so if I get off track, I apologize. So here's the 3D view of the building, and it can be manipulated like any other CAD model. And what we see is the incoming transformer that's feeding the electrical distribution system. And as we go back to that subset of the browser, we can see here's the transformer external to the building. Here's the main distribution panel. And as I select these, you can see the data that's been used in the modeling and subsequently information that will be handed off to EasyPower. So in the case of there's apparent loads, there's apparent fault current, there's some estimate of what's going on, but it's not been verified necessarily with an analytical tool. One of the elements I want to follow is EP3. So let's see if I can find it on my panel schedule. So if we look at the panel schedule for EP3, we see we have pre-selected some sizing of the breakers involved and some elements that don't seem to be correct or properly filled in. So we want to keep an eye on how that's handled in EasyPower. Okay, so let's come out of this. The export module from the Revit Play Store or Revit Store is, if you've downloaded it, in the add-ins selection. And what we're going to do is export to file. We can open it directly into EasyPower, but I want you to see what the import steps look like. So I'm going to start with a project that I know where it's located, just so I don't get lost. And I'm going to start with this 2024 RME basic sample, the suffix being Revit to EasyPower, EasyP. So it's already, I've done this before, so we're going to replace it or write over that label. Now I'm going to go into EasyPower and import that file. So in EasyPower, I'm going to start off with File, Import from Revit Integrator, and it gives me a step-by-step browser that lets me control what's going on. So first of all, I want to make sure I'm looking at the same folder and the same file that we both agree. So Revit 2 is EasyP. That's what I'm looking for. One we just generated in Revit. Then we're going to define all the default mapping based upon the information from Revit, or we could create a new configuration. We're not going to deal with that right now. We're going to create a new one-line diagram, or we can merge it with an existing one. Again, as changes are made, we may want to do this at some time in the future before we finalize the project. And then finally, here's an overview of what's about to happen. The inputs coming from that My Desk folder, my desktop folder. We're going to do a default mapping and import. And it's going to give me errors once we've done so in EasyPower. So I'm going to go through the import. It gave me a list there shortly of the elements that didn't have proper data, which looks like were all the transformers. Not too worried about that. And here's what the project import looks like. So EasyPower has drawn a one-line diagram based upon a guess at how the engineer wants it laid out. And you'll notice that as we zoom in, all the cables are number 12 AWG, which is just a placeholder, at least in the Revit world. Here's a number 10 AWG. The transformers, again, were flagged because they had incomplete data. Looks like there's no impedance ratio. But if we go down and look for EP3, we can open up the panel panel description and see that incoming's main lug. The branch is the only one there. And then here's the schedule that we saw in Revit. And again, there's default values. They do have each phase loading calculated. And if we look at the protective devices, they're only indicating this multi-case circuit breaker. Nothing else really has been decided. So in a typical world, I'd have to go through and size each of these elements based upon my knowledge of the loads that would be applied. But for now, I'm going to cheat and use auto design. EasyPower has a module we refer to as auto design that's rule-based. So if I come down and look at the options, it gives me an opportunity to modify the rules. First of all, from the catalogs available in EasyPower, there's 4 different manufacturers with 2 catalogs each. and then a couple of generic catalogs. And these are, we can discuss them when we get to it, but I'm going to start with Square D 2007 as a place to locate the selections of the components that I'm using in AutoDesign. When we select a component, we're going to base it upon the code factor amps, and then for multi-case circuit breakers and panels, we can either constrain how it's being analyzed, or we're going to size everything. Any motors that are in the system, we can select whether they're full load, non-reversing, or two winding, solid state, or whatever. Let's stay with full load, non-reversing. Let's go to lines. The tap rule is at 25 feet. We're going to show a three-phase 4-wire solution. If there's not a length indicated for a cable as it's set up, we will apply or equate a 99-foot by default. If there's not something designated in the file, this allows me to go back and search on the 99 number and then adjust anything as far as the final dimensions for each element. And then finally, we've got sizing lines based upon the short circuit test, the trip unit, and then the size is based upon the tap or plug rating. So we can use either or. When we're selecting a maximum pickup setting for a breaker, we're going to go to maximum available on the data sheet, and then the size for feeder breakers are going to be based upon the bus rating. Again, it's going to use these locked rotor multipliers for any motors in the system, and then based upon a voltage drop calculation being more than a 5% difference, it's going to, when that's the case, it's going to upsize the conductor by 20%. And finally, we're going to allow sizing on everything and not restrict what we're going to go for. So I'm going to save these rules. Again, I picked out a Square D catalog. There's no voltage in the import, so I'm going to use a basic utility icon at this point. Now, AutoDesign will only work on the elements I've selected since I'm doing this for the whole project. Let's select everything and then invoke AutoDesign. Now, again, what I'm expecting is a selection of Square D parts based upon a decision tree that I've established in the device library. And I'll look at that before we're through here. But as I come back to it now, I see my transformer based upon 480 volt to 480 volt requirement is recommending a 5% impedance ratio and a 500 kVA size. If we zoom in, we can see it's sized the cables now. Here's we have a 1/0. Here we have a single conductor 1/0. Here's a single conductor 4/0, and the like. It's got individual Square D part numbers for each of the breakers, and they're sized for the downstream load. It's got, now it doesn't know how to allocate the labels on cables specifically. So as I rearrange those, I can pull out the data block and the text block and stake it so that it remains there as I go through import and export. Okay, and then I want to go and look at a couple transformers. So here's a transformer. It's a step down from 480 to 208, and it's got a 2.9% recommended value, 4.4 for this one. Let's go down and look at EP3 again. Double click on the panel icon for EP3. Nothing's changed on incoming, but under my description, now my loads are still connected. But if I go to the protective device, I see I have a square D part number, device style, trip settings, interrupt rating, and all that's now in the database, including the size of the conductors and the links, which are what we got from Revit when we did the import. Yeah, if there's any questions, feel free to just jump in there and ask, because I may not be catching everything that makes sense. So I'm going to save this. So every time I utilize Auto Design, the tool gives me also a report called Auto Design Report, which will go through all the justifications for any decision that's made in this process. And so here's the discussion of transformer TP2A, KVA rating, the X over R, full load current, and the impedance ratio. And then this is what the basis for that recommendation is. Here's panel 2A. It says it wasn't sized because in the decision tree, I didn't have an entry for 450 amps. I'll touch on that when we talk about the device library. And it's a decision tree that we can control. So likewise, low voltage panel 2. Looks like we're having better luck on panel 2A, row 2, 1. So again, I'd want to pay attention to anything that's flagged. Red means it's an error that needs to be adjusted. Warning means may or may not be close to meeting the goal. Okay, so I'm going to close this because I have access to one of the generic files that has been tailored for this particular project. I'm going to redo this sizing exercise and pick out a different catalog for my listing. So if I go back to Auto Design Options, now instead of square D, I'm going to pick out generic 2, where I presumably will have less issues. So I'm going to click OK, invoke Auto Design. Color comes back to me. Now you can see that the values are a little bit different because I have a different decision lookup table, but now I have generic part numbers. My cables that I moved around staked, and my cable sizing looks like it's pretty much consistent with what we saw before. Yeah, and likewise on transformer sizing, which I would expect. Now if we go look at the contents of EP3 and the description, we can see nothing's changed on the load, but the protective device now is a generic designation, and it may be something that we need to go back and pursue based upon the quotes that come in from the contractor. Okay, so we've sized the part. Now we're ready to go. Well, before I do that, I'm going to look at my import window. So I have a little better luck now because I've tailored the decision tree. There's still a couple cables out there that I need to adjust manually, but I can deal with that. Okay, so I'm going to close this report. Now the first step to do, if you will, error analysis or missing data analysis is to try to go to short circuit focus. So I'm going to go to short circuit focus with the lightning bolt on the top center. I get a clean one-line diagram, which means I at least have a minimum amount of information in terms of terminations and connectivity to do a short circuit analysis. So I'm up on the top row. I'm going to do a half cycle, 3-phase bolted fault all the buses. And as I do, I get a bunch of colors and a bunch of numbers. And so what we're looking at is the fault current at each bus if that bus faults. So if this panel has a 3-phase bolted fault, it'll see 2500 amps from upstream. The total available current is the number on the oblique. The fact that these are equal is suggesting that there's no motor loads currently on the schedule for this panel. And we're looking at a half cycle worst case fault. So this number for each of these buses will be handed off when we do arc flash to the model for being the worst case available fault current. The other thing I want to do with short circuit is determine my equipment duty. In short circuit options, under my control tab down on the bottom third, I'm defining equipment duty as a comparison against a negative 10% times the ratings that we get from the data sheet when we look the part up. So it's going to flag a warning if I'm within that 10% threshold. And the way that works is when I invoke Smart PDC, equipment duty, I'm sorry, it applies that test and flags anything that fails to meet the criteria. So I don't see any problems on the lower part. See a problem with this bus or a distribution panel. And so I would want to generate a report that shows me what these specific details are. Under my SC reports, I'm going to create an equipment duty cycle, including all devices. It's only just, let's do it. Do it medium verbosity and apply. And as I do that, under my list of windows, I get an equipment duty report, and I can see the only problem that I find is that problem on the main distribution panel, and it has nothing to do, well, apparently there's one breaker that's being over-dutied. And the duty rating that we got off the data sheet is 10,000 amps. In a worst case scenario, it's going to be exposed to 13.4. So we're over-dutying the device by 30% or 35%. So that needs to be addressed before we go further. Okay, so let's now. So I'm not going to fix that now. We'll worry about it later. Now the next step would be coordination. As I mentioned, since we have a lot of multi-case circuit breakers, coordination is going to be pretty fitful. So I'm going to just use sequence of events to see what I can do as a spot check. So once I'm in coordination, looking at current, I can fault a single bus. So let's go back to my EP3, select it, fault it. And now what I'm seeing is that same current representation, the available fault current from upstream. And since there's no motor loads, that's the total available fault current to be considered for equipment duty and coordination. The tool makes available to me this little sequence of events icon on the second row. Once I invoke that, it turns this element to blue, meaning it's been analyzed. It's verified the connection with this panel. Nothing's flagging as far as being miscoordinated at the time. However, it's flagging up here to this panel, again, which has got embedded breakers. Here's a standalone breaker that's tripping at 21 seconds, and it's flagged red as being miscoordinated. So again, I want to look at a report. So if I look at my PDC options, bottom right-hand column, create a sequence of events report, come back and fault the single bus again, then under my list of windows, I'll see a sequence of events report, and it shows me now what the details are for a fault on that bus. So this is a multi-case circuit breaker. It's going to trip in 10 milliseconds. This is a generic 400 amp circuit breaker that trips in 5 seconds. The next one trips in 11. So this is relatively small current. And by the time I get into 480, it's going to be even smaller. And so I have coordination up through main distribution panel 3, and I have an issue then when we start having miscoordination problems above that. So there could be a possibility of fixing that situation. So that's a single bus. If I click in an open area and fault all buses, there's too much information to show on the one line, but my sequence of events report, which again is under my list of windows, it's going to show me the condition of every bus in the upstream tripping order. And I can see I have, at the upper end of things, I have breakers that are offending my sequential analysis here. So I'd save a copy of this. What this tells me, though, is I need to spend some time and understand what's causing commonality to the different buses. Now, just for purposes of this discussion, I'd save a copy of this report. Oh, William's asking an off-topic question, which I appreciate, is why would the symmetrical components be grayed out? And I'm assuming we're talking about short circuit. Short circuit reports. Are you talking about reports or one line diagram? Here, my text output, I can do symmetrical reports and display the current in phase or per unit. Now, what he asked, when I'm in short circuit, so what's grayed out? So I'm guessing the icons themselves are being grayed out when I'm in coordination. And what we're talking about here is these are the symmetrical positive, zero, and negative sequence parameters, and they're not being considered for coordination. I can't answer why. I can imagine several different justifications for that, but rather than guess on it, let me come back to it after some time to think about it. But nevertheless, when I'm in short circuit, those icons are available to me. If I look at current, they're not available to me. Yeah, I have to think about that one, William. Good question. Thank you. All right. So now that we know we have a coordination issue, I'm just going to try this for grins. And that is, I'm going to see if Smart PDC can deal with it. So I'm going to select the whole system, go into coordination, invoke Smart PDC. And so it's having issues with these elements, but for purposes of upstream coordination, it looks like it made some adjustments on these. So let's see what it tells me. So I was able to deal with the lower panels. And so in some cases it's saying it's unable to protect from thermal damage cables that weren't necessarily properly sized. So I have kind of a catch-22 because I had some cables in there that weren't sized during auto design. They're going to cause me friction or gas whenever I try to coordinate against damaging. So again, there's a little bit of a bad example, but it'll give you an idea of where you're going to address issues. Okay, so I've got my coordination done. I've got my short circuit done, my auto design. I can do arc flash calculations now. The Burning Man symbol on the top row. And looks like we've got some issues on these lower panels, which are primarily 208 volt because they're all behind a step down. So as you are probably aware, what's recommended under short circuit options, arc flash hazard tab, implement the 2-second rule for less than 250 volts. Make sure you're using integrated method in the 2018 version, excluding the main. Click OK. And then fault the buses again. Oh, I didn't see anything change. Oh, didn't take. I accidentally pushed the number, unpushed the number lock. So let's try this again. Okay, now I've got more civil results. And in some cases, I'm well within my 1.2 calories per square centimeter. So here we have 7 calories, 4 calories. And we may want to look at the actual fault current for some of these that we're not comfortable with. So we've done coordination, we've done short circuit analysis, equipment duty, arc flash. I might want to go through and see what's issues. Any questions on any of this so far? Okay. Now, so this is the extra added. When you look at the options menu, we recommend including Revit integration and PowerFlow as part of the basic arc flash combination pack, if you will. And because of that, I'm going to go to PowerFlow because it can catch overloading issues that may be the result of not adjusting the size properly on the cables. So now we go into PowerFlow, solve the equations, and what we're looking at is real and imaginary power. Now the problem is we don't have any loads on all of these panels, but the ones that we do, we see we're supplying 59 watts and 44 kVAR to this particular panel. Now the fact that these are red are indicated by these icons here on the top left. On the second row, we have overloads. We're showing overloads for current. They will be because this icon has been set. If we see mismatches between voltage, the second icon shows the voltage mismatch. And what that amounts to is we've told during database edit, we've designated this as a 208 volt panel, but when we run power flow, the per unit voltage is going to drop down to 0.92. So there's a mismatch between what we told that things should be and what things actually are. Now, this more than likely is a result of the lack of tab or adjustments on my transformer. And if we come back and look at my overloads, I can see my transformer is tapped or not tapped between 480 and 208. So consequently, we're getting voltage dropped out right at the transformer. Well, the reason I'm going through this exercise is one of the neat features about power flow is the ability to recommend taps to keep the voltage where it should be. So I'm going to go back to database edit. Let's go ahead and save what changes we've made. And even though there's not a load tap changer in this transformer by design, we're going to pretend it is and adjust the taps on the from side to hold the voltage constant on the to side. And so by doing so, it's going to come up with the calculations for taps recommended based upon my power flow. Same thing we're going to do here. We're going to assume that there's a load tap changer and what it should be set up. And then this will give us what the taps are that we need to make as fixed elements. So let's try this again. Go into power flow, solve the equations. Now we see this one's resolved its overload problem, by putting a tap on 0.453 volts, kilovolts, and then it'll hold steady the 208 side. What's going on over here is an overloading issue. And this is one of those cables that didn't get sized properly. So let's go back and fix that. And so it's a matter of dropping quite a bit more than it was rated for. So let's set this up as a 2 conductor per phase, size 250. I think I want 600 amps. So now again, this is not a recommended way to design stuff. I'm just trying to show the advantage of the tool. So I put in a cable that's much healthier. If we go back to power flow, do the calculations. Now I have, I'm close to the limit. It's a negative number, so it's still not being exceeded, but I'm within that 10% threshold that I was looking for. My taps look good. Now this may be a case where we normally run our transformers at 65%. So rather than leave them at 100%, which is how they were originally modeled, we might say, well, let's scale the downstream transformers to 65% and see how that handles my overload situation. And sure enough, that's good to go. Now, one of the things that's useful is utilizing the text reports under Power Flow, and these can be individual reports or total summary reports, and one of the most popular is to calculate the voltage drop. So if I come back to here, save it, voltage drop icon is this little one with the voltage down arrow. When I click on it, it'll give me the voltage drops for each cable and for each transformer. I'll also see it when I come back to my power flow summary. So here's my voltage drop report. So now I've got short circuit, power flow, arc flash, coordination. Let's take all that back into Revit. So I'm going to go back to my database edit, save all the changes I've made, go back to here and export to the Revit integrator. And so I can be selective about what elements we're sending the data back on. And I need to put this in a place I can find it. So again, it's be my desktop Revit. And it's going to be, the suffix is going to be exp2 Revit, which I've already done. So let's overwrite it. Let's go back to Revit. Now again, we're going to import from my Revit demo, and we're going to take in 2024. Now that it's got all that data back in here, as I pick out a specific element, you can see that the results from the EasyPower analysis are included in the description of that particular element. Now, some of this is going to be data that was at least set up originally in Revit, and so we might want to make sure that we overwrite those values rather than keeping the EasyPower results aside. All right, so let's see where EP3 ended up. Now, the one thing, so this is still a Revit value. We could set up to make sure we import over this part number name based upon the analysis that came back from EasyPower. Likewise, the rating would be something that we would be updating, and so that's just a note I want to make. So nothing's really changed other than potentially the size of the breaker. Okay, so that's the capabilities of the Revit integrator. Now, one of the things that questions that come up is that how do you put the one-line diagram into the Revit project? The way that's done is so we generated the file, the DXF file, when we created the import. So right now, I want to look at view. I want to look at drafting view right here. We can adjust the scale. And so let's just pick a size. As we do that, I think I picked the wrong size. Now, one more thing. The question usually comes up. So somewhere along in here, I got access to a electrical system that will show the one-line diagram. So it saves it in the file. Finally, the question about adjusting the configuration, the overlap, or the data that's pulled in and the way it's labeled. So as far as symmetrical current, when we import it and export it, we're looking at the EasyPower results. If we wanted to make this override an existing Revit name, I would just make sure I include that only. I don't create, I just import it. So the next time I import that file, it'll end up in the place that Revit's looking for it, that data. Okay, that's all I got. So one more thing I wanted to, if there's no other questions, show is you have access to these folders for these files that I just generated. If you don't have Revit, you can, let me go back to EasyPower. You can duplicate this whole exercise by, let me go to my start page, opening one line under your when you have EasyPower installed, it sets up the folders to look like this. And in the one-line folder, there's a sample subfolder. And in the sample subfolder, there's a Revit file. And therein lies the types of files you can import. So Snowden Tower, I think, basic examples of projects you can access. Okay, thank you all for attending. I can answer any questions, or you're more than welcome to contact me via email, and I hope you have a good day.